Yeah.
How does it feel like coleslaw? Did you buy recently?
Well, I got it through ASU. So I think they just ordered it from Microsoft.
Okay, good. All right. So I'll just get him started, then I'll run downstairs to get his folder.
Sure.
So, okay. So Nitesh is going to present story detection using generalized concepts. This master thesis, right? So they did this algorithm, they got some good results, they're writing a paper now. So I'll let him go over the details, huh? Yeah. Okay, Nitesh, you do it. I'll be back.
Hello everyone, good afternoon. Thanks a lot for coming, taking out time from your busy schedule. So my thesis work is basically related to text mining, data mining, and a little bit of machine learning. So the topic is story detection using generalized concepts. So you can see there are three things: so stories, and then we discover generalized concepts from the text that we have, and we use those generalized concepts to detect the stories. So we have the labeled data set already from the social science team, from Professor Foreman's team. So the text is like this. So I'll tell you what are stories. So any text or any paragraphs which match this condition, actors taking action leading into resolution. So basically some people or some community is doing something and it's resulting into some resolution, then we call it as stories. Otherwise the paragraphs is labeled as non-stories. So you can see here what's happening. After the Pagan army calmed the area, blah blah, the explosion of the mine planted by the Mujahideen against the apostates resulted in serious wounding to military soldiers. So basically the Pagan army is doing explosion here and it's resulting in wounding. And when the apostates tried to escape from the place, a third mine detonated, wounding in unknown numbers. So basically here also see wounding is happening. So this is something which we call resolution, and somebody is taking some action, actors are taking action. Other than stories, we have many types of non-stories like exposition, supplication, or this imperative words. But we are not very concerned about the classification of non-stories in this thesis research. We just call it as a broad category of non-stories. So we are majorly concentrating on detecting stories in this research. Now let's see what are generalized concepts. First, let me tell you this. What we do is, so these are basically objects and these are predicates. So in the natural language processing linguistic point of view, a sentence can be broken down into objects and predicates. So predicates basically say what objects are doing. So here, see, politician, ruler, tyrant are trying to abandon, change, negate law, principle, rule, Sharia. So this you can see as a negative change, and this object, predicate, an object is trying to establish a positive change. But again, we are not very concerned about positive or negative change here, but there is something these objects are trying to do here using these predicates. So these concepts are basically very important. We believe that these could be helpful in detecting the stories. If we can discover these concepts from stories separately and non-stories separately, and we can divide these concepts into discriminating features, like the stories have a different feature and non-stories have different features. These concepts could be used in classifying stories. So here's what we started with brainstorming. So we started on a note of finding a good similarity algorithm first, which can find similarity between the subjects, verbs, objects present in our data set, like the text. From each paragraph we extract subject, verb, object, and then we try to establish the similarity between subject, verb, object. first. That was our approach at the first place. So there's something, some algorithm called tensor decomposition, which basically is a tensor is a multi-dimensional array. So every text is projected in form of a three-dimensional array, and the full data set, full set of triplets can be made into a, you can say, a three-dimensional matrix where each dimension refers to one subject, verb and object. So this tensor decomposition is basically applying SVD to that three-dimensional array, reducing the dimensionality of that matrix. After you do the dimensionality reduction, you can apply a similarity algorithm to find contextual synonym. The approach is not very good here in this tensor decomposition because we started with a similarity algorithm and then we try to build upon it to do clustering. But to do a proper state-of-art clustering in this sort of contextual semantic web is not very good because it's not able to discover the concepts that we are trying to do. Then I tried to build a new similarity algorithm, which is just co-occurrence based similarity. Basically every word that is coming with some other word will count towards a similarity. So if two words are coming together with a word, it will count towards that word similarity. But again, that was not very effective, and the major breakthrough which we did was this bigram co-occurrence similarity and this bottom-up hierarchical merging. Before that, when we were taking the approach of similarity algorithm first, we tried to build many types of clustering like k-means, hierarchical, spectral, but that was not very effective. So we tried to move away from the state-of-art algorithms and build our own algorithm, which is, this one is for similarity and this one is for clustering.
Say, Nitesh, before you go on, so in tensor decomposition, it sounded to me like you said it wasn't very effective because it didn't work. Why again is tensor decomposition not effective?
Tensor decomposition is effective. What I said
but
is,
in this case, yeah.
Yeah. So what I said is we took the approach of using the similarity algorithm and then building upon it to do clustering, different sort of clustering, these clusterings. So these clusterings are not able to discover the contextual, like the concepts from the contextual synonyms.
Why not?
Because the clusters are good, but only the very frequent words, like the top words in the similar words here, like the very frequent words like kill, destroy, which are used many times in our data set, only those become very relevant while doing clustering. And the clusters that we get is very big, either very big or like the single clusters. But what we want is small clusters which can differentiate from themselves. So basically we took the very naive algorithm, building small clusters and differentiating from them. That's our approach at the second place. So let's talk about the system architecture. This is our data set, which is classified, manually labeled into stories and non-stories. Then we have semantic role labeler, which is labeling the paragraphs, paragraphs, which is extracting a triplet from the paragraph that we have, subject, verb, object triplets. Then we build a contextual similarity algorithm, and these two things, the subject, verb, object triplets and the similarity algorithm, will be used as an input to our merger engine. Our merger engine is, you can say, the core of the algorithm, which this thesis is all about. So I'll explain it later in the coming slides. Once we discover the concepts, we use them as a feature in classification of stories and non-stories. I'll explain them in detail. So starting with semantic role labeler, this is the parser that we use is ClearNLP, which is a part of Google's code developed by 3 different institutions. So what it does is, for every sentence, it will extract subject, verb, object triplets from here and many other things. But we concentrate on subject, subject P object, verb object, and object P object. Object P object is basically the prepositional object.